This is the moment in organic chemistry where everything changes. Up until now, we've just been responding to the reagents given. But today, we take control. We're not just following the chemistry anymore, we're dictating it. Our goal? Eliminate an alcohol. Sounds simple, right? But if you think you can just throw in a strong base, think again. So what do? We invent the conditions to make it happen. And I'm going to show you how. This is the E1 alcohol dehydration, and it's the turning point in your organic chemistry journey. Hey there, ninjas. If you are watching this video, you probably just finished up the substitution and eliminations chapter. If you're still struggling with substitution and elimination, I have one video where I'll walk you through the entire process in just 25 minutes. I'll link to it down below. So when you're presented with this reaction, you might have an idea of what reagents you're supposed to use. This is an elimination reaction. We know how to do elimination reactions. We should be able to add a strong base to do an E2 elimination reaction. But that will not work in this case, and I'll give you two reasons why. The first is that the alcohol itself has an acidic proton. If you were to mix this alcohol and sodium hydroxide together, the strong base would just deprotonate the alcohol long before it ever did an E2 elimination. That would ruin the base you were trying to use and ruin the leaving group you were trying to kick out. But even if you could get the hydroxide to attack the beta hydrogen, the leaving group that would have to leave would have to be OH-, and OH- is not a leaving group in substitution and elimination land. If you would like a refresher on what makes a good leaving group, I have a video that I'll link to down below. So if we can't use our traditional E2 reagents for a reaction like this, what are we supposed to do? What I'd like to prove to you in this video is that you now have enough chemistry knowledge to take a reaction you've never seen before and invent the reagents to make the reaction occur. That is a very powerful place to be. It's also kind of the whole goal of this course. This course was never meant to be a memorization course. Organic chemistry is actually a very logical science. If you've built a good foundation, you should have all the tools you need to predict future chemistry, to invent new reactions, to tell molecules what to do rather than just respond to the reagents given. So let's take a second to list the problems with this reaction as given and invent some solutions. The first problem with this system is that the leaving group is a bad leaving group, at least in substitution and elimination land. OH- hydroxide is too unstable, too strong of a base to be a leaving group, at least at this part of the course. The second problem is, even if we add a base, the alcohol has an acidic proton of its own, and a base would just deprotonate the alcohol, ruining the very reaction we are trying to perform. So how are we going to try and solve these problems? One of the things we're going to need to do is convert this historically bad leaving group into a better leaving group so that it can leave. Additionally, we're going to have to invent a different reagent other than a strong base. So let's invent some reaction conditions that allow us to solve these problems. First, if hydroxide is a bad leaving group, what would be a better leaving group than hydroxide? If this bond breaks and OH- as a leaving group is not a stable enough leaving group, what would be more stable of a leaving group than OH-? Water would be a more stable leaving group. Instead of OH-, if it left as H2O neutral, water would be a much more stable, much better leaving group. So what reagents would I need to invent to turn this from an OH- hydroxide leaving group into an OH2 neutral water leaving group? The difference would be the addition of one extra proton to that oxygen. We need to add an acid. We can add any generic strong acid. We're going to add sulfuric acid for this video. I have a separate video that I'll link to down below that talks about generic strong acids and what can go in this position. Adding sulfuric acid is an acid source, and so our oxygen on the alcohol can pick up one of these protons from sulfuric acid to get protonated to turn into a protonated oxygen, which will be a much better leaving group. Let's double check that we have all of our charges and carbons. This molecule has 4 carbons in both cases, and protonating the oxygen makes it a positively charged oxygen. Let's double check to see if this intermediate can be stabilized by resonance. This one cannot, and we should pause to see if this previous step was reversible. In the forward direction, we did an acid-base reaction to protonate the alcohol. All acid-base reactions are reversible. We just need to decide which side of the equilibrium is favored. We'll use pKa's, and our mnemonic weaker acid wins to help us do that. If you'd like a refresher on pKa's and acid-base equilibrium, I have an entire playlist that I'll link to down below. We're going from a mineral acid with a pKa of around -5 or so to a protonated oxygen with a pKa of around 0 or so. The weaker acid will win, the product side will be favored, and so this acid-base equilibrium favors the product. Let's just pause here at this point before we invent the rest of this mechanism. Why did we just protonate an oxygen like this? The problem we were trying to solve was that our leaving group was not a good leaving group. By protonating the oxygen, now if the bond breaks and this group leaves, it leaves as neutral water, a much more stable, much better leaving group than hydroxide. So as we're inventing these reactions, should we now add a strong base because we have a good leaving group so we can do an E2 reaction? No, we should not. One of the things we do as chemists as we invent new reactions is we have to watch out for compatibility issues. If we add sulfuric acid to make the leaving group a better leaving group, and sodium hydroxide to do the elimination, what's going to happen is that these two acids and bases are just going to neutralize each other and no reaction will ever happen. So we still can't add a strong base. We still can't do the E2 elimination. That means it's going to have to be an E1 elimination. In the E1 elimination, the leaving group leaves spontaneously to form the carbocation. Now that we've created a good leaving group, let's have it leave spontaneously so that we can see what that carbocation looks like. This is the carbocation that forms. Quick check to make sure we have all of our charges and carbons. Quick check, no, this intermediate cannot be stabilized by resonance. And let's talk about reversibility for a second. An important pro tip to keep up your sleeve is to remember that carbocations can do one of three things. Every time we see a carbocation, they can do one of three things. They can rearrange. Every time we draw a carbocation, we have to watch out for rearrangement. I'm sure you just talked about that in substitution and elimination land. If you learned the reactions of alkenes and alkynes before that, I'm sure you talked about rearrangement in that unit as well. We simply must always look out for rearrangement every time we draw a carbocation. This particular carbocation will not rearrange, but in the E1 alcohol dehydration, we do form a carbocation, so sometimes in the future, this carbocation will be susceptible to rearrange. The second thing that carbocations can do is elimination. That's the E1 reaction that we're trying to do here. And the final thing that all carbocations can do is coordination. Some kind of nucleophile can attack the carbocation to form a new bond. Some kind of nucleophile like the water we just kicked out. So yes, this process is reversible. If this water attacks the carbocation, that would just take us back to this protonated oxygen intermediate. Coordination we might know by another name like SN1, where we form a carbocation and a nucleophile attacks. We also see coordination in alkene addition, where the alkene attacks through Markovnikov's rule, and then something attacks the carbocation. These are the three things that carbocations can do, and we should be aware of them anytime we draw a carbocation. What we want to do in this case is the elimination. We've talked at length that we can't use a strong base to do this elimination. We're doing an E1 elimination, so we must be using a weak base. But what weak base could we use to do this elimination? We don't need to add any external reagents at this point. Notice what we kicked out as a leaving group. We kicked out water as a leaving group. Water is a weak base. We've used water as an E1 base in substitution and elimination land. We can use this water with this carbocation to do the E1 elimination. The generic strong acid that we added here actually solved all of our problems. It turned the alcohol from a bad leaving group into a good leaving group, and it provided us the means to have a weak base to use for the E1 elimination. So now our water can use its lone pairs of electrons to attack the beta hydrogen, collapse those electrons down to form our new alkene product. Quick double check that we didn't drop or add any carbon. We don't typically draw any resonance contributors for our products. And let's talk about reversibility for a second. The byproduct we generated is H3O+. In the forward direction, water took the beta hydrogen, forming the alkene, an H3O+ byproduct. So in the backward direction, this alkene would have to attack H3O+ to pick up the hydrogen and form the carbocation. Have you seen any reactions between alkenes and H3O+ before? If you've had the alkenes and alkynes chapter, then yes, you have. This is the setup for the alkene hydration. If you haven't, don't worry. I've got a video that I'll link to down below, and you will see this reaction soon. An alkene reacting with H3O+ is one of the most prototypical reactions of the alkenes chapter. Yes, this is very much reversible. This last step of our mechanism follows Zaitsev's rule. Recall from substitution and elimination land that Zaitsev's rule says that when we form an alkene, we'll form the most stable, most substituted alkene possible. And this reaction adheres to that convention. This is the mechanism for the E1 alcohol dehydration. And I want to congratulate you ninjas. We invented this reaction that we have never seen before. We looked at what we needed to have happen, how we could make those things happen, and then invented the reagents that allowed us to do the reaction we were trying to do. Way to go. I'm very proud of you. Did you notice that every step in this mechanism was reversible? It's true. Every step is reversible. We can take this alkene and work our way backwards to the alcohol. An alkene reacting with acid and water is the alkene hydration that we learned about in the alkenes chapter. This entire process is reversible, and this is an equilibrium reaction. So how do we control which side of this equilibrium will be favored? We go all the way back to Gen Chem and we use Le Chatelier's principle. We generate water in the course of this reaction. So if we swamp the system with water, that will push the equilibrium back towards the alcohol. If we limit the amount of water, notice no water was added in our reagents. If we limit the amount of water, that will drive the reaction towards the product. Since this is an elimination reaction, we can also remember that heat generally favors elimination, and if we heat this reaction up, we'll favor entropy and we'll favor the alkene product. There's one final thing that I want to warn you about with this E1 alcohol dehydration. We started with the problem that the alcohol was a bad leaving group, and we solved that problem by protonating the alcohol. This is actually not the most generalizable way of turning an alcohol into a good leaving group. I want to warn you about something called the primacy bias. The primacy bias says that the first piece of information you hear sticks in your brain the most, and you have to work to overcome that first piece of information. This is likely the first time that you're seeing an alcohol be turned into a good leaving group. So you're now primed to think that if you need to turn into a good leaving group, no matter what the situation, you should add a strong acid. And that's not generalizably true. This E1 alcohol dehydration goes through a carbocation which might rearrange. If we needed to do an elimination that avoided rearrangement, this would not be a good way to do that elimination of an alcohol. If instead I wanted to do an SN2 reaction, many SN2 nucleophiles are strong nucleophiles and strong bases and would be incompatible under an acidic condition. So while this is the first way that you might be seeing how to turn an alcohol into a good leaving group, it's not the best. It works really well for this reaction and it's cheap and easy to do, but there are better, more generalizable ways of turning alcohols into good leaving groups for whatever you want to do with that alcohol. Adding a strong acid really only works in a handful of situations, one of them being the E1 alcohol dehydration. So just file that away. And as you move on in the course and learn how to turn alcohols into halogens and alcohols into sulfonates, those will be much more generalizable ways of turning alcohols into better leaving groups. This is the reaction card for our E1 alcohol dehydration. The three-phrase sentence for this reaction: an alcohol reacts with a strong acid to form an alkene. We need to know that three-phrase sentence and all possible combinations. An alcohol reacts with a strong acid to form an alkene. A strong acid turns an alcohol into an alkene, and an alkene is made when an alcohol reacts with a strong acid. Some notes for this reaction: it works for really any generic strong acid. As I mentioned, it is not the most generalizable way to turn an alcohol into a good leaving group. And do be careful, it goes through a carbocation intermediate and you have to watch out for rearrange. Some tags for this reaction: it is regioselective, it follows Zaitsev's rule. It is also stereoselective, it will favor trans alkenes over cis alkenes, which is another application of Zaitsev's rule. And it is redox neutral. The alcohol and the alkene are both at the 1 CZ bond oxidation level.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.